Okay, today we're going to talk about exponential growth and decay modeling, which basically is just applications of exponential growth and decay. So, we have some models here. The mathematical model for exponential growth or decay is given by, it is f of t equals a sub 0 e to the kt. Or you may also see it as just an A equals A sub 0 e to the kt. Okay. So what do all of these things mean? Well, right here you can see, it says in your notes, if k is greater than 0, it's the growth rate, then you're going to grow. So if it's a positive growth rate, obviously it's going to grow. You're going to get this right here. If your k is less than 0, then you're going to have decay. All right. But what do each of the letters mean? I'll put that in these blanks up here. So your a sub 0 is always your initial amount at time 0. Initial amount at time 0. Okay. And then A is your amount, AMT for amount, and T is time. And K is your growth rate. So K is the growth rate, T is the time, A is the amount, which you can think of as the new amount, and A sub 0 is initial amount at time 0. This notation is for anything. V sub 0, A sub 0, M sub 0. Anytime it has a subscript of 0, it's the initial amount, initial mass, initial velocity. You'll see that a lot in a physics class. Okay. So here's our first example. The equation A equals A sub 0 times e to the kt models the growth of deer population in a small local preserve. If the initial population is 14 deer and the population grows to 20 in 4 years, find the value of k, which is the growth rate. So we need to underline the important information. The initial population is 14 deer. So right away, A sub 0 equals 14. The population grows to 20. So A equals 20, and it's in 4 years. So T equals 4. And it says find the value of K. So K equals K. That's what I'm plugging in. So now I just plug into this equation right here. A equals A sub 0 e to the kt. You should always copy that, write it first. You'll memorize it that way. And then you know exactly where to plug things in. So this is 20 equals 14 e to the, it's the 4k. We always put the coefficient before the variable, so it's 4k. Then you solve. Okay, so we're going to divide both sides by 14 because we need to isolate the exponential first. So when we do that, divide both sides by 14, we get 10/7 equals e to the 4k. And now we're going to take the natural log of both sides because we can't possibly write 10/7 as a power of e. So when we do the natural log, we end up with natural log of 10/7 equals, now remember one of our properties, natural log of e to an exponent is just the exponent. So this is 4k, and now we divide by 4. When you type this into your calculator, just make sure you end the parentheses. So it should look like natural log, parenthesis, 10/7, then divide by 4 is how that should look when you type it. So you get 0.0892 equals k. The next one. So it's a little trickier. use the exponential decay model to solve. So half-life. This is a huge application of exponential growth and decay in this growth rate. So the half-life of carbon-14 is 5,730 years. If 16 grams of carbon-14 is initially present, how much will be present in 5,715 years? So you can see it's very close to the half-life, so it should be very close to half. I can think of that in my head, but I still need to know exactly what it is. So we're going to have to go through a few steps here. Initially, we know that A sub 0 is 16. That's what we're starting with, 16 grams. We also know that the time we're eventually looking for is 5,715 years. Okay. Now what we don't know is the K. We don't know the growth rate for that. And we know how much our A is for this, but this is a weird one because of half-life. First we have to figure out what the K is. Okay, so any half-life is going to have, any amount that you would start with is going to be half in 5,730 years. This one right here. Okay, so to start out, we're going to say that A equals, actually A is what we don't know. So we have two unknowns here. We can't solve if we have two unknowns. So first we have to figure out the K. So first, find K. Alright? And since what we know is half-life, we're going to use A equals 1/2 of A sub 0. A equals 1/2 of A sub 0 is what we're going to start with. Okay? So here's what it'll look like. I'll make that red. So for A equals A sub 0 e to the kt, what we know is we're going to have half. So 1/2 A sub 0 equals A sub 0 e to the 5,730 k. So right now we're trying to figure out the growth rate for 5,730 years, no matter how much we're starting with. We know we're going to end up with half of what we're starting with. And now solve. So divide by A sub 0. That's gone. So we get 1/2 equals e to the 5,730k. Okay. Do natural log on both sides. So we end up with natural log of 1/2 equals 5,730k. Divide by 5,730. And so if you type that in correctly, your k equals, it's negative because it's decaying, it's negative 0.0001297. Negative 0.0001297. Okay. So now we need to do part 2, which is where we use this k value and all of this information we were initially given to figure out this specific situation. If we start with 16 grams, how much are we going to end with in 5,715 years? So now we'll put all that in. Okay, so I'm going to use the bright green in case I go into the black over here. Okay, so A equals A sub 0 e to the kt. Let's plug in all of our information. So we don't know A. I'm trying to figure that out. We're starting with 16 grams, so 16 e to the negative 0.0001297, and I'm going to run out of room. That's times 5,715. So these two numbers right here are your exponent getting multiplied together. So you want to make sure that you put that in parentheses when you raise it to the power. Raise the e to the power. And if you type it in correctly, you should end up with A equals 8.014. So final answer, in 5,715 years, comma, 8.014 grams will remain. Okay, so but you had to figure out the k first. Logistic growth models. So logistic growth models are next. What logistic growth models are for is when you know that there's an exponential pattern, but there's a limit to the exponential pattern. Some things just can't possibly go on forever. And that's what this is for. Logistic growth models are when there is a limit to the growth. When there's a limit to the growth. Here's a picture showing that. So if you've taken pre-calculus or calculus, this kind of looks like the integral symbol. There's a reason for that. It's limits. The mathematical model for limited logistic growth is given by, so we have f of t equals, if you can't see that very well, it's c over 1 plus a e to the negative b t is what that is, behind the a. Equals a. Where a, b, and c are constants, and c is greater than 0, and b is greater than 0. And then your curve looks like this. So it's increasing some, and then eventually it's going to have to decrease, because there's just a limit to the growth. So it has to slow down eventually. Okay. So let's look at an application of this. The following logistic equation models the number of people who become infected with norovirus on a small cruise ship off the coast of Alaska. How many people will become ill by the second week if T is given in weeks? So it just lays out the formula for us with all the given information plugged in. So basically that means there's 500 people on the ship right there. If there's 500 people on the ship and they contain it to the ship, you can't go past 500, so it's not going to grow forever. Okay, so we know that T equals 2 weeks. So essentially we just need to plug that into the equation. So f of 2 equals 500 times over 1 plus e to the negative 1.5 times 2. You might want to multiply this together first if you can. It's less to type in a calculator then. So 500 divided by 1 plus e to the negative 3. And you just type that in. Be careful. Make sure you include parentheses. Have to include parentheses around that whole thing. Okay? And when you type that in, you should get 476.29. And just kind of ask yourself, does it make sense to round up to the next person or not? It doesn't here. So I would say after 2 weeks, 476 people become ill. And that's your logistic growth model. So the rest of them that you have are a few more examples. The art of modeling. This gives you a diagram of the different curves. So here's your exponential. This is if b is greater than 1. You can see it's rising. Here's your exponential. We've got 0 is less than b is less than 1. You're coming down and approaching that asymptote, decaying. These are your logarithmic models. You have that vertical asymptote. You're going away to the right. This is for a positive a value. Here's your negative a value. You're starting high against the asymptote and coming out to the right, down and away. That's all drawn in there for you, but basically the scatter plot gives you those patterns. And so this right here, this is your home practice. So see if you can figure out the growth rate for the squirrels. And then you have a second one, and then it's multiple choice. Now you need to make sure that you have some work here. I want you to actually work out this problem, but your answer should be in these multiple choice answers. And then you have a logistic growth problem next that I would like for you to try. Okay? So those are your 2 home practice problems. This is a logistic growth. You're basically just going to plug in there. So try this. Please do the work. Thank you.